Hey, and welcome to the first Fun Friday event of the Oktoberfest 2021. And this is a special one to me because I spent a lot of time in the Computer History Museum in California when I was living there. And I love the exhibitions there. And I'm
Hey,
honored to,
welcome to
ooh,
the first Fun Friday.
I have a feedback here. And I'm happy to introduce Dag Spicer, the Senior Curator of the museum, to you. And I just quickly hand over to him so he can say some words before we start with the live viewing session of the video we prepared. Dag, up to you.
Thank you, Kevin. I'm Dag Spicer, Senior Curator at the Computer History Museum, and I'm really happy to be with you today. We're going to be watching a little video tour that I did of our main exhibition in our main campus in Mountain View, California. And I do invite you, just ahead of our show here, to please drop by anytime you're in, once we open. Sorry, we're closed for COVID, but we will be open hopefully in the near future. And I invite you all to come, and please let me know that you're coming, and we will put on a special reception for you. So my background is electrical engineering and the history of technology, and I'm going to take lots of questions at the end, so feel free to think of things to ask during the presentation, and I look forward to hearing from you at the end of the show. Thank you.
Thanks, Dag. Let's get started with the video.
So the first gallery that we're going to look at in Revolution is about the abacus. And Revolution is actually one of 17 galleries. Don't worry, we're not going to stop in every one. Each one devoted to a certain theme or topic in computing, like punch cards or calculators or supercomputers or analog computers. Those are all galleries that feature just that technology and objects related to it. Every artifact, every gallery, I should say, also has a video station at which people can stand and watch and hear the inventors speak. So the narrative of the museum, of course, is the museum's narrative. We write the labels and so on. But if you want to hear the inventor's voice, and in many cases we have long lost footage of rare footage of inventors speaking about their inventions available right in front of the very objects, so people can get a multimedia experience there. So the abacus is the first gallery that people see. It's actually called calculators, and the abacus is, of course, one of the pretty much the first thing people see when they walk in. And we show that this is an ancient device. It's really of a class known as a counting frame, and it goes back even as far back to, so there were Sumerian abaci in 2500 BC, as well as abaci in Egypt and Persia and all over the Near and Middle East, and as well as Asia. So if we take a little turn to the left here, so if you can see just off to the left, whoops, sorry. These are aids to calculation. And here we show with the ever-present gaze of famous mathematicians through history, like Pascal and Leibniz and so forth, and Babbage. Just their eyes, though, to kind of give it a little design element. Here you see slide rules, linear and circular, an interactive slide rule right in the middle there that people can actually practice and understand how a slide rule works on their own. Very, it's kind of an indestructible museum one. And as well, we have some beautiful brass and glass gunner's rules, sectors, compasses from the 17th and even the 16th century that people can see in the drawers underneath those. So really going as far back as we can. This exhibit is meant to show, remember, the first 2,000 years of computing. So we're going back as far as we can. Off to the right, you can see it as a Kurta, the famous round cylindrical mechanical calculator designed by Kurt Herzog, a Holocaust survivor. There's a Pascaline there, and Napier's Bones, an interactive off to the side, the far right there, where you can learn how to use Napier's bones. Now here's a favorite, I think, of Paul's. He really liked this one, the Antikythera Mechanism. And I don't know how many people have heard of this, but it's actually rewriting the entire history of technology, because this device, which is from basically the 2nd century, demonstrates, or within it shows technology that should not have been, that was not discovered until the 1500s in Europe, or perhaps a bit earlier. So the Antikythera Mechanism is actually an eclipse prediction machine that uses a series of geared wheels that interrelate and follow ancient Babylonian star cycles in order to allow the user to predict the motions of the planets and when there'll be eclipses. So you think about the time when this was made, AD, 2nd century AD, and it was made in the tradition of Archimedes, actually. And so the weird thing is, it's quite alien in its state of technological advancement. As I said before, we didn't see clocks or other mechanisms of this level of sophistication for another 1500 years. So it really stands out as an oddity. I should point out that this was discovered initially in 1900 by Greek sponge divers who went to a little island called Antikythera. There's an island called Kythera and another one called Antikythera. And as they were sponge diving there, the diver came back up gasping for breath and said there were all sorts of dead people on the bottom and dead horses, and he was very afraid. And initially people thought he had the nitrogen bends and he wasn't, in a proper frame of mind. So went back down and saw basically one of the most important finds of classical statuary in history. Something like 40% of all existing classical Roman statuary comes from this one site, the Antikythera site. 36 marble statues of people like Julius Caesar and Julius Caesar, and also the other thing I wanted to point out is you can see this little station here in the middle. This is that video station that I was talking about, where you can actually see and hear people talking about the mechanism. And we actually had a custom movie made for us by the journal Nature, which describes the mechanism, how it works, and cites world authorities on the mechanism and its history. It's still being decoded, is sort of the honest truth. You can see the original in the Archaeological Museum in Athens. And I think there are about 80 parts, and some of them are falling off. But this is probably why we say the first 2,000 years of computer history, even though the abacus, the Sumerian abacus, is older. We really had the Antikythera device in mind when we thought of the first 2,000 years. Okay, punch cards. Punch cards, of course, were the mainstay of electronic digital computing throughout the 20th century. And it began with this modest machine known as the 1890 census machine. This is a replica, by the way, I should be right up front about that, wooden replica built by the master craftsman Roberto Gotelli, who was actually built a lot of the models of Leonardo da Vinci for various world fairs and museums in the 60s and 70s. So he built this for us. And you can see essentially how it works. You put the census taker goes out in the field and asks questions. It's then brought to a clerk who, if you look at the device on the left here, this is called a pantograph. The clerk then encodes the answers from the census taker as a series of holes in the using the pantograph. At that stage, the data is now machine readable. So that's a rather cosmic transition in the history of information processing, to move from manual to machine readable computing. So the Hollerith machine was made to, you basically put the punch card in this little press here, close the press, and inside, mapping every possible hole position of the punch card are discrete cups of mercury, as in the element mercury, the liquid metal mercury. On top of the little waffle iron press there are little rods that are connected to one side of a circuit. The cups of mercury are connected to the other side of a circuit. Where there's a hole, the rod goes through, contacts the cup of mercury, and kicks over the corresponding counter, which you see on the face of this machine, one position. So it's a tabulator. So at the end of the day, you just read your dials and you've got the sum totals of all your statistics. They were able to do the census in about three years using this technology. And the previous census, the 1880 census, had just been finished with months to spare. So they really needed to automate. And Hermann Hollerith, a German-American engineer and census contractor, came up with this system. Hollerith's patents, of course, became the basis for the IBM company, which started out as the Computing, Tabulating, and Recording Company in 1911, and then changed its name in 1924 to the International Business Machines Corporation. So all of IBM's initial sorry, not all, but most of IBM's early important patents were Hollerith patents. In fact, as you may know, these punch cards were sometimes called Hollerith cards for that reason. Hollerith apparently got the idea from a couple of sources, watching a train conductor punch out tickets, which had a physical description of the people occupying the seat. So if the little punched out ticket that the conductors had punched said there should be an elderly woman here and there's a young boy, there's something amiss, someone's moving around the train or whatever. The other source is the Jacquard loom, of course, which used the Jacquard loom add-on, which was added on to existing looms to provide a punch card driven pattern generation mechanism. And anyway, that's a long discursion on punch cards. One more on punch cards, which I want to bring up, is the PowerSamus machine. And I brought this out especially because this is an English audience, or a Welsh audience as well. And I wanted to point out that this was a special project actually done by the Botanical Society of the British Isles to map all the flora of the British Isles. And so using citizen scientists in the best amateur tradition who would go out and fill out surveys of local flora, they encoded these in punch cards and then generated these maps. And you can buy the book on Amazon, the actual atlas as well. And that was all done in this particular one in the 60s, using equipment very similar to this. And the PowerSamus cards, of course, these ones are only 40 columns, but PowerSamus made cards in multiple formats, up to even 130 columns. A little nerd moment, if you're interested, the PowerSamus machines use mechanical feelers, while the IBM's systems read their cards using electronic systems. Like I say, that's of only interest to the most diehard gearheads. Okay, Enigma. I'm not going to speak much about Enigma because the people on this call are probably so much more better acquainted with the machine. But what I did want to do, draw your attention to, was just to the left of Enigma, you see a pulley wheel. This pulley wheel, which came from an English chap named Toby Harper, is said to be one of the few, or maybe the only remaining piece of a Colossus. And it's from the bedstand. If you see right beside here on the wall, we've blown up a picture of the bedstand that was used, that ran the tape at, I think it was 5,000 characters per second, something like that. Some incredible number of miles per hour while it was looking for matches. Now, here is the King Kong of the system that I really want to get into for everyone, the SAGE semi-automatic ground environment. So probably most of you have not heard of this. And in fact, even most Americans have not heard of this. It was an immense military project to create essentially a shield over North America, a defensive radar-based shield whose purpose was to detect incoming Soviet bombers coming over Greenland and the eastern seaboard and dropping an atomic bomb on New York or Washington. Those are really kind of the threats And so Sage was made up of 23 blockhouses stationed across the United States and one in Canada in North Bay, Ontario, which is in fact where we got ours. It was the last running Sage system in 1982. Sage was built out of 2 giant computers. Each blockhouse had a duplex computer, twin CPUs, each with 30,000 vacuum tubes, so 60,000 vacuum tubes in total. The duplex CPUs actually was a stroke of genius, because the machine itself had a downtime of less than an hour a year, which is simply unheard of at this time in terms of reliability and mean time to failure for a computer, especially one using vacuum tubes. So a lot of preventive maintenance and a lot of love and care to keep this system running. Now, what you see on the right there is actually an operator station. And you might see just in front a little silver object that's called a light gun. And so an airman would sit in front of this screen, or you use it with using this light gun, and wait for targets, which were basically the local radar picture of their sector was projected on their screen. All the known flights in the United States commercial aircraft system were punched in to Sage. So it knew what was supposed to be in the sky, and could therefore, by subtraction, tell you what was not supposed to be in the sky, the scariest Soviet bombers. So this workstation on the right here was actually used, just dozens and dozens of these, row upon row of airmen looking through. There's actually a built-in cigarette lighter and ashtray in each of these, so it was quite a boring job. As if there are any private pilots in the audience, I can think of the closest analogy to their job is what pilots sometimes experience, which is hours and hours of sheer boredom punctuated by moments of total terror. And as they were waiting for these incoming bombers that never came, they did have some false alarms. For example, in one case, someone left a training tape on the system during a shift change, which moved the whole country to an increased defense condition, because it took a while to discover that. So anyway, Sage actually cost more than the Manhattan Project. That's how big a system it was. And it was developed from basically 1956 or 7 to about 1961. By 61, it was fully deployed across the United States. The problem is that by the time it was all deployed, the Soviet Union, and indeed the United States, had developed ICBMs, the Intercontinental Ballistic Missile. Sage, unfortunately, could not keep up with something that fast. It was targeted, it was meant to handle slow-moving bombers. And so essentially the system was rendered somewhat obsolete. Now, in the case of all good military systems, sometimes if the enemy doesn't know the limitations of your systems, it's safer to assume that it works. And in fact, that is sort of what seems to have happened. It happened again with Star Wars, with Reagan, which on a technical level was probably not possible. And some more milestones of Sage. Sage is actually the outgrowth of the Whirlwind system from MIT. Sage is Whirlwind 2. So that fantastic computer that we looked at initially, the one for which core memory was developed, and essentially really the earliest electronic digital stored program computer, and was the MIT Sage, MIT Whirlwind, of which Sage is a direct progenitor. And what you see in front of you, just as we wrap this up, is actually probably less than 1% of the system. So if you can think of 60,000 vacuum tubes and the space that would take. What you see on the left here is known as the shower stall, and it's actually a 16K kilobyte magnetic core memory for Sage. So that gives you an idea of how big 16K memory was in the late 1950s, early 1960s. So the granddaddy of all mainframes for the 1960s, of course, was the IBM System 360, which IBM introduced on April 7th, 1964. That was just a few weeks actually before Ford announced the Ford Mustang. So it was a good year for sort of classic American, technology. And the big thing about the 360 was it was actually a response to an internal crisis at IBM in which there were 5 or 6 or maybe even 7, depending on how you count them, mutually incompatible product lines. They had punch card equipment with metal Queen Anne legs and mixing in with like modern styled tape drives, and it was just the whole product line was kind of a mess. And unfortunately, IBM being a sales driven company, it created a crisis for the salesmen because they didn't know what machines to sell, and customers often called IBM asking for a computer, and they get 3 or 4 different IBM salesmen calling them trying to sell them a different system. So clearly IBM had to do something to resolve this internal crisis, and what they came up with was actually a family of systems known as the IBM System 360, which when it was introduced, when they finally shipped in 65, came out in 5 different models spanning a 40 to 1 performance range. So everything from a small, departmental type server to something big enough to handle an insurance company or a bank, and several models in between. The great thing about IBM, what I forgot to mention too, with these earlier computers, you had to write your own software, your own compilers, your own editors, your own everything. Every time you bought new hardware, you had to rewrite all your own software. And it was only later on that manufacturers also, eventually decided they should start providing software. You really had to roll your own this is in the 50s. So when the 360 came out, it became one of probably the most successful computer architecture of all time. And I say that with some caution, because I know there are a lot of architects. The x86 architecture is pretty powerful, but the fact is that in terms of the value of transactions processed by 360 code and the 600 billion lines of COBOL code that are legacy COBOL code that are still out there and that are running essentially 360 or 370 code, but on the latest Z series mainframes, that's an architecture that has stood the test of time. A 60-year-old architecture, and it can still run essentially with a few modifications, much of the same software. That was exactly their intent, was to preserve customers' investment in software. So you could move from the small, low-end model up to the high-speed, high expensive model, and essentially with, it wasn't perfect, but you could essentially use the same software. And that just shook the industry. And of course, most of the people here probably know of the expression Snow White and the 7 Dwarfs, where IBM was Snow White, had 70+% market share, and the remaining 6 or 7 companies of Burroughs, NCR, Control Data, RCA, Honeywell, and so on, had to share the remaining 25 or 30% among themselves. And I think almost all of them went under eventually, trying to compete with IBM and in the mainframe sector. This was just to finish off, this was a huge gamble for IBM. They essentially poured about $5 billion into it. This is 1964 dollars. At the time, they were a $3 billion company. So that was really sticking their neck out. They went out into the markets and got financing and pulled it off. Okay, another amazing IBM product, the 1956 RAMAC, the Random Access Method of Accounting and Control. Now, the name RAMAC doesn't really, it refers better to the system they built out of this, which was kind of an inventory control system. But essentially, the RAMAC is the world's first hard drive. And I'm very careful with the F word, which, as we call it at the museum, the word first, because you're almost always wrong. But in this case, I can go out on a limb and say this is the world's first hard drive, and we have it. It's composed of 50 24-inch diameter discs, coated with magnetic oxide and spin coated. And you can see on the left the the arm, which goes up and down, in and out with the read-write head, and reads and writes data to RAMAC. But something that really may surprise you is we actually demonstrate this in 1956 technology. We demonstrated every Wednesday at the museum, or will again once we open up. And we actually found 45-year-old customer data still sitting on some of the platters. So that was kind of interesting. We run the demo, we control it with a laptop, and you can actually, we cycle through the read write to heads and read and write, show how it moves up and down. And so this was basically the start of the entire hard drive industry. They still follow this basic technology, a spinning disk with a read write head that moves across or in and out. And this began IBM's long foray into mainframe hard disks, which they called, oh, sorry, I'm blanking out on the name. Sorry, DASD, Direct Access Storage Device, DASD. They didn't call them hard drives, they called them DASDs. So anyway, RAMAC was the start of IBM's dominance in the DASD space for the next 2 decades, until smaller companies and the microcomputer hard drives and mini computer hard drive companies started competing. This is one of my favorite computers. This is the CRAY 1 supercomputer made in 1976 by American engineer Seymour CRAY. There's a see-through, if you look at the bottom, you can see we put some see-through plexi on the bench there. There's a circular bench around the computer, which is circular itself. If you look at it from the top on, it forms the letter C, which I guess is C for CRAY. But there's actually a great technical reason for it being circular, and that is that all the wire lengths can be made shorter. If you think of the way it is right now in a circle, and then if you were to expand it into the usual linear square, cabinets side by side, all of a sudden all the wire lengths will get longer. And in a machine of this speed, wire lengths matter. In fact, the machine every wire is cut within about 1/16 of an inch. They're essentially transmission lines. And what you see on the bottom are the power supplies. The it's a -5 volt supply, because this is ECL logic, comes in at 1200 amps. So that gives you a nice idea of how much power this took. And cost about $100,000 a month to operate in the 70s, $50,000 in air conditioning and electricity, and $50,000 in maintenance and sundries. What we have on the left here is actually really interesting. This is Seymour CRAY's original notebook for the CRAY 1, and you can see he uses a very unique Boolean method. I'm sorry I didn't zoom in on it, but he actually trained his staff to go right from Boolean logic diagrams to building circuits. There was no schematic. There are no schematics in a CRAY computer. Quite remarkable. Now, of course, the CRAY 1 was a legendary machine, not only for the size, its unique shape, but just for its raw speed, which, computer engineers and architects at the time were just agog at the speed of this machine. They could not believe how fast and, the connoisseurship that Seymour CRAY showed in the design and the balance of the system and how it's designed to work. The 3 largest applications for this system, and indeed for most of high performance / supercomputing during this era, which is the Cold War. Without a Cold War, I don't know if CRAY computers or CRAY research would have been such a robustly functioning company. And the 3 main applications during the Cold War for these supercomputers were essentially cryptography, weather forecasting, and sorry, just let me check my notes here. Oh, bomb design. Yes. So designing nuclear weapons. And so all the national labs and the Department of Energy had CRAY 1s, and they made, I think, over 100 of them at about $10 million a piece. You also needed an existing mainframe to connect to. So if you think about the math coprocessors that we used to have, and with the 8087, the 287, the 387, the early x86 days, that's essentially what this is. It's a floating point coprocessor. Our next stop is the PDP8, the Classic, which you can see on the right here. Excuse me. And on the left, I wanted to bring your attention to the little sign here. It says mini computers, and it was actually a Digital Equipment Corporation salesperson known as John Lenk, L-E-N-K, from Britain, who said something about, from the land of mini skirts and the Austin Mini comes the mini computer. And so we thought we would do that. We showed a woman wearing a mini skirt and someone kind of a go-go boot here on top of a PDP-8. The PDP-8 was, the word mini computer was kind of new, and I think it did actually reflect cultural usage at the time. People talked about mainframes, but that was about it. So they sold, this machine was really remarkable for a number of reasons. One, it cost less than $25,000, which was the discretionary budget for many departments, either at companies or universities. It was $18,500. That meant that all of a sudden, a gigantic market of people could afford to buy these without having to go up the chain for authorization. It was still within this, and they did that very consciously to keep the price down. The reason they could keep the price down was, among many reasons, was the use of this rather amazing computer-controlled automated wire wrap machine called a Gardner-Denver machine that did all the backplane wiring automatically. So no longer were there assemblers hired to wire wrap, and with all the errors inherent in that process and the bad connections and so forth. So they were actually able to drive the cost way down. And at the time, for an equivalent mini computer, you'd probably spend about $100,000. And so this at $18,500 was just a blockbuster. And what it allowed people to do is, aside from using the mini computer as a tool for, scientific research or departmental computing, that you could do word processing on it, and sort of rudimentary word processing on it, was in process control, actually. So building intelligence into factory processes was one of the early and most important applications of mini computers. And in some cases, those mini computers, we just got offered a mini computer, an old Honeywell ProDAC control system computer that was running a steel mill. It just came offline now. It was installed in 1973, and they're offering it to us now. So that shows you the longevity of these systems. They're very robust. And we also have, just off to the left, you can't quite see it, but we have as another example of how you can build intelligence into objects using mini computers, is we have actually a brain surgery cart just to the left. And that it's showing essentially PDP-8E performing a fast Fourier transform in real time of the EEG signal from the patient's brain. And the surgeons can use that as they operate for diagnostic purposes. Okay, I have to admit, this is one of my favorite photos. We have an exhibit on Moore's Law, which we like to show with this illuminated graph here that shows you the big skyward trajectory of Moore's Law. And we happen to have Gordon Moore came by the museum one day, and our staff photographer said, would you mind taking a picture for us? So we're pretty happy about this one. Gordon Moore published in 1964 in the journal Electronics, his first, didn't call it a law at the time, but his first observation that was actually related to the cost of integrated circuits, the cost to produce them and the marginal extra cost. But people latched onto the transistor count. And so from then on, it's kind of been about the transistor count. And you think of the trillions of dollars in wealth that have been created from generated by the technology behind this simple law. It really is remarkable. And so we thought it deserved its own gallery. Just, everything else is object-based, but this is actually a principle, an abstract concept. And we thought it's so important. We need to call it out. So actually this exhibit, which was finished 10 years ago, stops at 10 billion transistors. We're now at 35 billion. The new Xilinx Vertex FPGAs are 35 billion. And in fact, there's a new wafer scale engine by a company called Cerebrus, which is like the whole wafer is the chip. They don't cut it out into little with a diamond saw and package it in little chips. The whole wafer is a chip. It has 2.6 trillion transistors, and 850,000 CPU cores. So that's quite something. The Xerox PARC Alto, and I'm keeping an eye on the time here. I know we've got to get going. This is a remarkable machine as well that is the progenitor of so much we use today, including the computers we're watching this webinar on. The Alto in 1972, keep that year in mind, 72, 74, thereabouts, had a graphical user interface, email, word processing, laser printing, Ethernet, a bitmap display that was meant to duplicate a sheet of paper, a removable disk, a 3-button mouse, painting and graphics program, a file manager, a chess games and pinball, and a Star Trek game. All of this in this one machine done at the hothouse of Xerox PARC with some of the smartest computer scientists in the country came up with this machine. And of course, the legendary tale, which I'll be very careful how I cite it, but let's just say that Steve Jobs saw this machine at Xerox PARC and was inspired to apply some of its principles, including hiring some of the people who worked on it to come over to Apple and work on the Lisa, which became the Mac. So the Alto is really an incredibly important machine. We all owe our graphical user interfaces to that and to a couple of other machines, but it was the first one to really tie it all together. We have an Apple I computer, which is the very first product of Apple Computer, the Steve Jobs, Steve Wozniak, and Ronald Wayne, the third employee who people usually forget about. We actually got Woz to sign it for us. And this came out in 1976. It was a single board computer, had a built-in, I think it was 4K basic. You could put in either a 6800 or a 6502 CPU, depending on what was cheaper at the time. And they made about 200 of them. There are about 50 left. And part of the reason for that is that the Apple, when it came out with the Apple II, the follow-on product, offered a trade-in on the Apple I. So those took out a bunch of them, took a bunch of them out of circulation, and they unfortunately probably trashed those. You may have seen the current prices for an Apple I. They've gone as high as $1 million, which is unbelievable. The original price was $666. So because I think people see it as the sort of object of Apple, so it's sort of acquired this mythic status. Now, based on the success of the Apple I, Steve Jobs said, well, what if we designed a computer for the consumers rather than for people who like to solder? And so that actually came out and was known as the Apple II, and which I won't show, but I think most of us know what that looks like. And it came out in 1977, which is known as sort of the Big Bang in personal computing. 3 machines came out that year: the TRS-80, the Apple II, and the Commodore PET. All came out within months of each other. Second to last object is the Google Server Rack. This is a really fun object. There's an electronics store here called Fry's, which is, sadly, they just went under. But they were sort of the go-to place for hobbyists and engineers in the Valley to go pick up parts. Like if you needed, the joke was you could buy chips and potato chips at the same store. You could buy a Z80 and a box of Pringles, a can of Pringles at the same place. Anyway, these Google Server Racks here were designed by or built by the 2 Googlers, Larry and Sergey, and their team, who went to Fry's to buy a bunch of what are called PC 104 format personal computers. They're small. They're like maybe 8 inches by 8 inches square, entire PCs on a little board. And so Google took a bunch of these, put them on a rack, put a very thin sheet of cork board, that is in cork, as in a cork bottle, a wine bottle underneath each one. So the whole thing is really kind of a fire hazard. Nonetheless, the thing worked. That they have two network switches above, which map out faulty nodes in the search in the array of personal computers. And the cool thing is, if you did a Google search in 1999 or 2000, it may have gone through this very rack. So that's something to think about. And our final object is the interface message processor, which is the device that allowed the first mainframe computers to connect to each other on the ARPANET. So actually, the concept of an interface computer was first proposed in 1966 by Donald Davies at NPL to connect NPL's because we have disparate mainframes in different locations. We need kind of a common box that can talk to another common box, which in turn will talk to the custom hardware on both ends. And that was the IMP. Essentially, it's a gateway, or what we call now a router. It's built like a battleship. And again, some of the very earliest internet and ARPANET communications went through this. It was built by Bolt, Beranek, and Newman, a firm in Boston, and has inside a hardened Honeywell 516 mini computer. So again, the mini computer running, being used as a host, sort of, or I should watch what I use the word host, but as an interface, a way to connect different hosts to each other. Now let's just wrap up and look at the future. The museum going forward is going full on digital, as well as keeping all our beautiful, wonderful objects, of course, in the historical collection. But what we're trying to do now is really step up our IT systems and the way they work, and specifically the way it would affect you in the outside world, is to create what we call essentially an API to our collection. So what we're calling OpenCHM is to make our historical collection and archives more visible and accessible to a global audience. And so we're going to build some hooks and APIs for people to share content and pull content directly from our collection and use it in whatever ways they want. And that'll also allow us to share and compare collections across institutions if, as what we're hoping will happen, the technology that we're developing with Torrentia, a company in Toronto, and Microsoft, is a combination of digital asset manager and collection management system. And we're going to develop that internally and then release it to the world so everyone can use it if they want. Now, I know it's a big, changing your museum database system is a big deal, so it's not for everyone, but we're trying to contribute to the discipline of making our collections more obvious to the world. It's really what it's all about. It doesn't do any good if it just all sits in a warehouse. So just a final call, please visit us. I would love to personally show any BCS members, give you a personal tour and show you around the museum. And we can stop and have a coffee or a tea and talk about computer history. There's so much more. And we've just taken a really whirlwind guide through the place, and I hope you enjoyed it, and I look forward to your questions.
Cool. I hope everyone enjoyed the video. It was exciting as always. I mean, I was looking in the chat most of the time, and then like people are just going crazy on everything you said, Dag, and we're discussing all these kind of things. Some of them even have written their first programs and some of the newer machines there. I mean, me personally, I grew up in a time where my first program I developed was on an i3 Intel processor. So this is way out of what I did back then. But yeah, I mean, really, really interesting. You want to add something before we jump into the Q&A?
Thanks, Kevin. No, not really. I was watching the chat as well, and that was great. I was very informative and entertaining at the same time. So I really appreciate people taking the time to comment, for sure.
So let's start with the Q&A. I'm just grabbing the chat over here. All right, let's see. So Rachekar Verma is asking if there is a chance to access these computers.
Access as in booting them up and interacting with them?
I would guess so, yeah.
Yeah, for the most part, no. And the reason is museums have a tradition of being pretty conservative when it comes to actually intervening, as we call it, with the objects in our care. The main thing we're focused on is the future. And so we don't want to do anything that will impair later generations' understanding of the object. And sometimes if you do restorations, if you don't do them carefully, you end up changing the object in ways that people can't unpack later. And so they don't know what is original and what has been changed. Having said that, we have two awesome functioning computer experiences right now. Two of them, one by IBM and one by DEC, Digital Equipment. And the IBM one is called the IBM 1401 Demo Experience. The 1401, I didn't mention it, but it was a computer that was just came before the 360. But the amazing thing is, it was actually almost more successful initially, because by 1950, half the computers in the world were IBM 1401s. And so we have one running, and we have two of them running, in fact. So anytime you come by the museum, you can punch up your own cards. You can punch your name in a punch card and submit it to the computer. The computer will print it out on a giant piece of paper, like a banner for you, for example. So there's some fun things you can do. And again, this is 1960 hardware, and it's running perfectly. We have a team of engineers that keeps it running constantly. And then the other experience, just to wrap up, is the DEC PDP-1 experience. And we chose that machine because it portrays a different style of computing. So the IBM machine is a batch oriented system. So you get a bunch of jobs together, usually multiple jobs together, and you submit them all at once. There's no real interactivity. So, you deal with your IO device is a punch card reader and writer. So there's no terminal or anything. So the PDP-1 does have a terminal, and that came out in the same year, essentially 1960. And so we put these two demonstration experiences side by side to show the two styles of computing at the time, batch versus interactive. And you can come actually there's certain days of the week that we run them, but you can come in principle at any time and run jobs on them, interact with old timers who used these back in the day, punch your own punch cards. So you can still have that great old timey computer experience if you drop by.
So DJ is asking what is your favorite exhibit item in the Computer History Museum?
Yes, well, I get that a lot, and I would have to say it's the Enigma machine, a German encryption machine that was used a lot in World War II. The reason is it's very simple. It's essentially a flashlight circuit, but if you consider its impact on world history, there are a few objects on display, and we have 1,200 objects on display. So it can take, there's a lot to take in there. That's 1% of the collection, by the way. The German Enigma machine had just a massive effect on human history, and as did its decoding and that's kind of where the Alan Turing story begins, and at that point as well. Cool.
I'm just going through the chat here. Let's see. Ian is asking. He would love to know much more about the behind the scenes of the museum, and if you have plans for any new upcoming exhibits, like mobile, for example.
Oh, that's a great question. If you send me an email, I can. If it's just like a small number of people, I don't mind giving you kind of a behind the scenes look around at the museum. It's kind of on an unofficial basis. Here I am telling, like 200 people about it. But anyway, be happy to show you that. Technically we the location of the objects we're pretty discreet about, just because for security reasons. But if you're in the area, I would definitely show you there. And what was the second part of his question? I forget.
If there are new exhibits.
Oh, new exhibits.
Planned, yeah.
Yeah.
Like a mobile one.
Right. There are no new exhibits planned for the next 6 months, I would say. That's our time horizon right now. And the reason for that is COVID. The exhibits are, exist in a physical space that has to be safe for people to visit. So having said that, we are doing some virtual exhibits coming up, and it's going to be a little surprise, so I can't tell you anything more about it right now.
That's good. We love surprises. I mean, that's got to be like that. We don't have any questions here, but we have some nice comments. I cannot read the name as it is in Cyrillic, but he is saying, watching this from a new computer, it made me think what a great path engineers made back in the times until now. So that's a nice comment here. And then we got another question from Abab Andy. JCL was awesome. What was the sword utility? Sync sword or something like that. I remember you could make the job steps execute based on the RC from the earlier steps. Okay, there you caught me a bit out of my depth there. Okay, sorry, not quite parsing that, but I don't even know what that question means. But sorry, that's not horrible.
Well, I have a question for you. As you went through, and we saw the pictures of like the Sage and the IBM 360. From the video, it's maybe a little hard for everybody to tell. Are those you physically have those in the museum? Those are those replicas, or are those originals, or are mock-ups? What were we seeing there?
Oh, I'm so sorry. My gosh, everything you see is real.
Okay, good.
Yeah. Oh, geez. I wish I had said that at the beginning. No, and they're absolutely, utterly real. Yes, real atoms, not just bits.
Excellent.
Yeah.
Excellent. Cool. Another question is, how can we participate to virtual exhibitions in the future?
By participate, I mean just like as sort of a passive.
If there like anything planned from the Computer History Museum side to offer like public virtual exhibitions or something like that, where you can just like maybe I would guess like in a 3D environment just roam around or something like this.
Or how can people be notified when you have them?
Or that, yeah.
Yeah, the best way to get notified is to just sign up on our list, and you'll get updates on every aspect of a museum's activities. Sorry, the first part of the question, what was?
Yeah, just how or if there are any virtual exhibitions planned.
Oh, virtual. Yeah. So there are virtual, yes, online only, and it's the same exhibition I was telling you about. Having just to connect though with what I closed the discussion on, which was this sort of API / I like to joke and just call it a museum compiler, but it's not a compiler. But I kind of like the idea of essentially people will be able to come to the museum and make their own exhibits. So that's kind of a cool thing. And then, it's all new stuff, because essentially, there's kind of a challenge to curatorial authority, and at large, as you probably noticed, authority of any kind is being challenged these days in the world, right? Whether it's science, whether it's politics, so that affects, curators like anyone else, right? We make knowledge claims, and people are free to criticize them or not, right? And so the difference between people who do it for a living and those who are not is that we tend to be more aware of our own shortcomings. So that would be the downside of giving people a tool to create their own exhibitions, is like they could create sort of nonsense, like the iPhone came right after the Hollerith machine or something, and whatever. But that's the way the world is going, where we can't really regulate how people are going to mix and match and combine our assets into their own stories. So that's the direction when you talk about virtual exhibits, and whether you'll be able to be a participant rather than a more sort of generally passive observer, where you go and you're sort of presented with things to look at and watch and read. This is a really hands-on thing where you're in the driver's seat telling the history. There's good and bad parts to that.
It's true.
Yeah.
If I may ask, so there was discussion in the chat as well that there are some kind of computer museums around the world, big and small. So I'm curious, is there any like organization that connects all these computer history museums around the world? Do you have any active exchange of maybe, you know, some items between these museums or any other form of cooperation around the world?
Yes. So the cooperation, I would say, is mainly, there's no real umbrella organization that, you know, there's a thing called ICOM, which is the International Committee of Museums. So that's for all museums, right? Not just computer museums. And around the world, like in Europe and Asia and North America, all museums, from art museums to, you know, music museums to computer museums, or a tiny slice in there somewhere. And so the way the relationships work is they're really personal between curators. So you know, we all know each other in the profession, and there's really only like 20-25 people who are really, you know, computer history is a pretty small, granular discipline, endlessly fascinating, you know, or I wouldn't be involved in it, but still, I do appreciate that it's, you know, when you flip up a bit and talk to normal people, for example, you realize, yeah, this is pretty specialist knowledge. But anyway, so all of which to say, that's how we do it. We form personal relationships. We ask other museums, like I just got one, I'm on the board of a museum, two museums, as well as a curator at my own museum, one in the United States on the East Coast and one in Ukraine, in Kiev. And they actually just sent us a wonderful Soviet era. Oh, wonderful. All right. The Soviet era, you know, it's the Computer and Software Museum. Do you know that one in Kiev? It's maybe not, but yeah, we just got this. They gave us this beautiful personal computer, and so that's going in the collection. And so that's exactly how it happens. Is, you know, they can find these kind of computers like from the Soviet era much more easily than we can. So we exchange. We can find things for them. That's how how it works. It's pretty informal.
Great. Thank you so much.
Oh, thank you.
I have a question for you, Dag, if that's okay.
Yeah.
I have another question, rather. I was really lucky to be able to go to the Computer History Museum, and my favorite exhibit was the digital VT100 terminal. And I want to know if it's for sale and how much you want for it.
Really? Well, yeah, we don't sell our objects.
No, I'm just kidding, but I just want
okay, just kidding. Yes,
bring it to people's attention, because
yes,
it's the holy grail for me.
Oh, is it the VT100? They made a lot of them. It's very canonical, that's for sure. Yes, and of course it survives in emulation as well, you know, still. So
that's why it's so important. Every terminal, software terminal we see now is basically has, you know, that's its mother. Yes, and yeah. Okay, well, I'll have to keep looking then. Well, they do come up, you know, believe it or not. We I would say 98% of what we get, maybe 99%, is a donation, which no strings attached, just and then maybe 1% or even less than that are purchases of the museum, from which among which we include eBay as a source, believe it or not. There's some remarkable things you can find on there. Yeah. Yes, that's the only thing I have an alert on eBay for, which is a VT100 terminal. Yeah, you'll find one, but it will be sought after. pretty sought after, I predict. Yeah.
Thanks, Doug.
Yeah, you bet.
So I had a quick question, Dag. I had the pleasure of seeing Ed Barnes speak at a college graduation ceremony back in the 90s. And he talked about his time inventing the Altair. So I was curious if you could share anything about the Altair that you know, and also have you met any other inventors and what it's like to talk with these guys that did things at the time they probably didn't think were historical?
Oh, that's interesting. Yeah. Well, the Altair, boy, there's so much you can just sort of spin out and, encompass so much history just from that one sort of point in time. One of the things I like to bring out is, in a way, the Altair pushed or incubated the independent software industry, the ISVs, independent software vendors. And the way it did that was when the Altair came out, it was $397. And a company founded by two Harvard students, Bill Gates and Paul Allen, and their company was called Micro-Soft. And they went and they built a little basic interpreter for the Altair, and they sold it for $495. And the medium was paper tape. So remember back then, very few people had glass teletypes, as they were called. They had teletypes, real teletypes, because they were surplus in the 70s. And a lot of hobbyists were able to buy these for a couple of $100. And they made excellent IO devices. They gave you hard copy, and you could type to the computer and it could type back. They even had two dual color ribbons. So you could have, your text to the computer in black and the computer talking back to you in red, for example. And so what Bill Gates figured out, though, was that computer clubs around the country, like the famous Homebrew Computer Club here in Menlo Park, people were literally copying these paper tapes, just running copies off on their teletypes and throwing them to each other as it's pirating. Okay. Throwing them to each other in this big auditorium filled with other Altair users. And Bill Gates heard about it, and he wrote this famous letter called A Letter to Hobbyists. And in this letter, Bill Gates said, hey guys, software costs money. He goes through, I had to hire all these people and pay rent and electricity and, buy computers and stuff like that. And then essentially the point he's making is software has value. And that, believe it or not, at the time was a really dramatic, it wasn't news to people in the mainframe space, but people in the personal computer space, and to some extent the mini computer space, because a lot of public sharing of programs in that space, kind of expected software to be free. And so it was at that point with Bill Gates' letter to hobbyists that he kind of put a stake in the ground and said, I'm going to try to make a business out of writing software. And, you're not helping. So please pay for your software. And I don't know how effective it was, but the point is, it was printed in Byte magazine. So a lot of people saw it, and it was kind of a shot across the bow. So that's kind of my moment for the Altair. It's not so much about the hardware. It's almost, what it sparked on the software side, this whole ISV industry, where people saw Bill Gates' letter, other potential ISVs saw it and went, okay, maybe this is something, the barriers to entry are so low. I mean, for $1,000 or something, you could become a developer, maybe even less than that. And that to me was like a huge point in the history of computing. Software has value. And, if you look at Silicon Valley now, it's not Silicon Valley, it's really Software Valley. I mean, the vast majority of the wealth being generated in Silicon Valley is through software, not hardware.
Awesome, thank you.
Yeah, you're welcome.
So if you got a little bit, a little bit more time, there's an interesting question from David Romero about becoming a curator of such a museum. I mean, you said you have the background in electrical engineering. So how did you get from being an electrical engineer to being a curator at the Computer History Museum?
Well, if you look up how to be a curator, you'll see I didn't take that path. So it's just I basically I worked in industry as an engineer for about 10 years, and then I was always interested in the humanities as well, and history especially. And so there was a special program where I was going at University of Toronto on the history of technology. And so I did a master's in that over there. And then I came to Stanford to do a doctorate in the history of technology. And after a couple of years, what my supervisor told me, hey, check out this opportunity. There's a guy named Gordon Bell. I don't know if that name rings a bell, but if you look him up, you'll be impressed. He's the father of the mini computer, essentially. He's the vice president of engineering at Digital Equipment Corporation. And so I met Gordon, and he said, he kind of gave me the Steve Jobs speech to Scully. He says, do you want to do something interesting with your life, or just, stay at Stanford? So he told me about this museum, and it was just like, man, this sounds pretty tempting. It didn't pay very well, but at the time, and it was a real shoestring operation. But what got me were what attracted me were the quality of the people involved. They were like people of like Seymour Cray stature involved with the museum, like serious industry pioneers, computer pioneers. And then the other thing was just the collection. The collection, because they had started in the mid 1970s, was just unbeatable. There is no collection like it in the world. We have first generation machines, for example, that there's literally only one of them, and we have them. So we can tell a wonderful story of computing. And so how you become a curator, sorry, to get back to your question, is you need some domain knowledge, and so that was where the engineering came in. But then you need to be able to write. So curators write a lot, and we describe objects a lot. And like if you give me a coffee cup or something, I could write a paragraph about it, right? And that's kind of what you do. A lot of that, a lot of short sort of writing. You write a lot of labels and a lot of mercifully short things usually. So occasionally you have to do it right along thing. So the short answer is that's not possible. The long answer to your question is that it's kind of a fluke, but if you want to set your mind on becoming a curator, you can definitely do it. First, just get the domain knowledge, and then you don't have to go through museum studies. You can if you want, but as for curators, it's not such a plus. It's really the domain knowledge that sets you apart.
Makes sense. Thank you for that answer.
Oh, sure. Sorry it was so long.
No, it's great. It's great. I mean, I have a lot of comments here saying it's amazing to just listen to the stories. It was a great session, and it was super, super interesting. And I wanted to thank you personally from SAP and our team that you had the time, or you took the time to join us today and be there and answer the questions of our community. That was really amazing. And I bet you have a ton of people visiting your museum as soon as it is possible again. And with that, I want to close today's session. And I hope everyone had fun. And I see you next time, or for the next Fun Friday event next week. And with that, thanks again, Dag. And
thank you.
Hopefully see you soon.
Yes, my pleasure. See you soon. Bye-bye.